Class, I wanted to make a video of a popular homework question that you encounter when asking about optimizing or minimizing and maximizing certain quantities using quadratic functions. So in this particular example, this is one that you might see in a type of calculus class in the future. It says a wire, so imagine just a long wire like here, that is 48 centimeters long, so a certain length, is cut into two pieces. So maybe we cut it in half, maybe we cut it in like a third the way. We're not really told that part. We just know it's cut into two pieces. So you have two different pieces of this wire. So one is one length and the other is the other length using the whole wire. For example, maybe you have 20 centimeters and then 28 centimeters, right? You could cut that in any way you wish. But once it's cut, it's going to have both pieces bent in order to form two squares. So what you could be talking about here, let's say you cut the wire and stop, let's say here, okay? So this wire here could then form one square. Let me make it a little bit longer just for the sake of argument here. Maybe make one longer than the other, just say we see what's going on here. And you bend it, right? And so this wire here, we could say maybe represents x. Okay, so that's the length of one of the, or not x in general, I apologize. That could be the total length here of that blue wire. And then I could say, well, when I fold it into a square here, each side would represent, these are 90-degree angles if it's a square, each side would represent the same distance, because that's the definition of a square, right? Right angles at all four corners, and each side is the same length. So I could use x, let's say, for that length. And the reason I erased x here was because if that side is x, then so is this side, and so is this side, and so is this side. Otherwise, it would be a rectangle if they had different side lengths, right? So if it's a square, all four have the same length. So for example, maybe this was 20 centimeters that we cut. Then this would be four items, four lengths, which add up to 20, and they're all the same. So they'd all be 5, wouldn't they? 5, 5, 5, 5, etc. Okay, so that's what I'm talking about here. So this is actually the 4x, if you will. X plus x plus x plus x. But the area of that little guy, area is length times width for a rectangle or a square. It's x times x in this case. So the area of that square here would actually be x times x, or x squared. So I noticed that its area here would be x squared, if you're talking about the shaded area, okay? Because x times x would give us that area, x squared. But what would be left for the other part here? Well, if you cut into two pieces, the other piece could be like a red wire, let's say. And again, it might be that they're exactly the same size. We don't know yet. That's why x is an unknown amount. But whatever was used up here came from a total of 48, right? So if this part was the part that we've already used here, right? The part that we've already used here, then that means that this part here was 4x, right? So let's see what we've used here. So this was originally 48, but then you had 4x that we've used here. Okay. So what remains for our other piece? Well, if you used 4x and you started with 48, this piece would be the 48 minus the 4x, wouldn't it? It would have to be 48 minus 4x, because if you combine those two, the 4x's cancel and there's your 48. So when I look at my rectangle that I would draw from, not my rectangle, my square rather, from folding this wire, maybe it's smaller, maybe it's larger, maybe it's the same, we're not sure yet, but we get another square when I fold that wire into 4 equal sides, and each side would be 48 minus the 4x's that we already used. But that's each side, right? There's 4 equal sides, so we'd have to divide that total by 4, since we have all 4 sides here to talk about. Just like here, we had 4x in total. We divide by 4, so we each have x. So if I divide that by 4, what do I end up with for each side length of this little square? Well, 48 divided by 4 is 12, and 4 divided by 4 is 1, so I have negative 1x or negative x. So each side here would be 12 minus whatever that distance was. 12 minus x, 12 minus x. And again here, this is 12 minus x. And you can see if that makes sense, right? If you were to add x plus x plus x plus x, that's 4x. If you were to add 12 minus x, 12 minus x, 12 minus x, 12 minus x, the 12 four times is 48, right? So you'd have 48, and then negative x, negative x, negative x, negative x, that's negative 4x. So 4x minus 4x, wipe out, and you're back to 48. So it does make sense. Now what would that mean for your area, though? Well, it was easier when it was the blue little one, where we did x times x. The area of that guy would be x squared. But the area of this guy here, his area, would be its length times its width, so 12 minus x times 12 minus x, or 12 minus x squared. And you could actually FOIL that out. So now when they ask you in this first part of the problem, now that we visualize what's going on here, when they say, could you find a function that would give us the total area enclosed by the two squares? So the area of the first blue square, for example, would be, so the total area would be your area of your blue square which we got was x squared, right? X times x. And then your area of your red square would be side here times side here, or side squared. 12 minus x squared is really 12 minus x times 12 minus x, right? If I do that and I FOIL carefully, 12 times 12 is 144. 12 times negative x is negative 12x, and then it happens again. So if I get two copies of negative 12x, I really have negative 24x. And then if I do negative x times negative x, that becomes a positive x squared. So this is the area of our red square. This was the area of our blue square. So when I want to combine the two areas, how much have I covered between the two squares? Well, my total area then, area depending on x, is going to be the area of the blue square, so that would be my x squared, plus, total means add them together, right? The area of my red square, which is this guy here. So that would be, if I put my like terms close by, x squared minus 24x plus 144. And when I simplify that, the total area enclosed by both squares would be 1x squared plus 1x squared, which is 2x squared, minus 24x plus 144. Now, why do I want to write a function this way? You might think that seems very, very weird. Okay, I understand the feeling. Well, the beautiful part about writing this total area function the way we have, now we have in terms of just one variable x, so we don't need to necessarily know the length and the width. As long as we know the length of one of the squares, right, we would then know the entire area enclosed by both squares together. Notice also the type of function that this is. We've been studying this in this unit. It's a degree 2 polynomial called a quadratic function whose leading coefficient is positive 2. So this tells us it's a parabola, doesn't it? Opening up. And we could find its vertex, which would, in this case, the vertex would be our minimum. Now that's helpful because they're asking us in the next part of the problem to find the side length which minimizes the total enclosed area. So to find that minimum, now we need to remember the vertex formula. You could also complete the square if you prefer to get it back into standard form, but vertex formula is easy enough. One thing some students do is if they recognize that all three terms of this quadratic function are divisible by 2, they can factor out that 2 to make their numbers a little easier. But you're welcome to jump right into the formula. So when I'm talking about minimizing or maximizing quadratic functions, I should always think vertex. This point here. This is our minimum if I'm opening up, and it's our maximum if I'm opening down. And you can tell that by the sign of the leading coefficient being positive. It opens up, so therefore the vertex is a minimum. So the vertex formula, if you remember, you can have your notes out here, is that to find that ordered pair, HK, H is negative B over 2A. So in this case, the opposite of B, here A is the coefficient of x squared, B is the coefficient of x, and C is the constant 144. So the opposite of B, the opposite of negative 24 is a positive 24. So you're welcome to write negative, negative, and then change the sign, or you can do that part in your head. Then divide by 2a. Well, a is 2, the coefficient of x squared. 2 times 2 is 4. Feel free to write 2 times 2 if that helps you in your notes. Dividing here, I'm getting 6 as my answer. So it looks like my vertex is 6 comma something. 6 represents the x value of the vertex, and x in this problem was this length here. So now I know that this should be 6. Well, that kind of answers the whole thing if you think about it. If that's 6, because this is a square, it's a 6 by 6 square, isn't it? Which means I've used up 4 copies of 6 on this square alone for its perimeter. 6, 6, 6, 6, or 4 times 6 is 24. And if I started with 48, then this also must be 24. So this square is also 6 by 6. And you can check that if you plug in your 6 right here. 12 minus 6 is 6. So this is actually a 6 by 6. So basically they're the same, which means each of them has an area of 6 times 6, or 36. So the total area enclosed is 72. But I can also notice that, to answer that last question, because they said here, what is the side length which minimizes the total area? It'll be minimized when this side length is 6, so 6 by 6. But in the last question it says, what is the minimum? When a problem asks you, what is the minimum, they're really looking for the k value of your vertex. So to find the k value of your vertex, remember what you do? To find k, you plug back in whatever you got for h as the x value of your area function. So area when x is replaced with a 6. So let's take a look at what that is. It's 2 times 6 squared minus 24 copies of 6 plus 144. So let's do our order of operations carefully. PEMDAS here. We're going to take our exponent before we multiply. 6 squared is 36. And 36 times 2 is 72. 24 times 6 is 144, but it's negative here. And then we have a positive 144. So you can kind of see what happens here. These cancel, don't they? Negative and a positive 144, leaving me with 72. The area is in terms of square units, right? So this is square centimeters. This would be the minimum area that would be enclosed in this square plus this square added together. So the minimum area that we're going to end up with is 72 square centimeters. And that's actually because we end up with 6 by 6 squares in both cases, each producing 36 square centimeters for area. Now, it's not always the case that they're going to be the exact same size, but in this case, based on the premise of the problem, it does turn out to be that fact. Well, I hope this was helpful for you. If you have any questions at all about optimization problems, please don't hesitate to reach out to me. I'm here to help. Otherwise, happy practicing. Remember, math is not a spectator sport. I'll see you next time.